4차 산업혁명 기획 14주 2차 시간을 시작하겠습니다. 챕터 16은 우주기술입니다. 국제우주정거장에서의 혁신에 대해서 나사의 스토판 책임과학자는 다음과 같이 얘기했습니다. 국제우주정거장 건설 이래 다양한 분야에서 수많은 연구가 진행되었거나 진행되고 있습니다. 이 중에는 사람의 건강에 대한 연구도 포함됩니다. ISS는 무중력 연구를 할 수 있는 다양한 다목적 연구실과 특수 장비를 제공합니다. 미세 중력하에서 인간은 다양한 생물학적인 영향을 받는데, 예를 들면 면역계 및 혈관계의 변화, 골밀도 및 근육 손실, 시력 감퇴 등이 있습니다. 나사와 국제 협력 파트너들은 이러한 영향을 단축하기 위해 노력하였으며, 이러한 노력은 우리가 지구에서 겪는 질병 치료에도 도움을 줍니다. 여기서 우주의 스페이스 스테이션이 어떻게 동작하는지에 대한 동영상을 보도록 하겠습니다.
The International Space Station is the largest man-made structure in space. It was built in pieces and then launched into space and assembled in orbit. In this video, I want to give you a detailed look at the station. We're going to look at each module in the order that they were assembled. We'll look at the countries involved and the future plans for the station. So if you're ready, let's go build a space station. The International Space Station, or ISS, took many years to become a reality. In 1984, the United States announced a project called Space Station Freedom. Here's some drawings of what the original station might have looked like. It was never actually built in its original form. There were lots of redesigns, and its funding was almost completely cut by US Congress. Then in 1993, after several other countries were brought on board, the name was officially changed to the International Space Station. 5 years later, construction begins in space. I'll show you the complete construction process, but first, let's learn a little bit more about the station. This is the ISS as it looks today. It's mainly used to conduct science experiments that can only be done in space. There's usually 6 astronauts on board the station. They generally switch out about every 6 months so that no one spends too much time in space. The station is about the size of an American football field. It's located just outside the Earth's atmosphere. This is called low Earth orbit. It's not very high up, considering that some satellites orbit way out here. The ISS only takes about 92 minutes to orbit the Earth. That's about 28,000 kilometers per hour. Over time, the ISS will slowly lose altitude. If nothing was done, the station would eventually burn up as it re-enters the Earth's atmosphere. To prevent this, the station must be periodically reboosted to stay in space. The main countries now participating are United States, Canada, Russia, Japan, and many countries from the European Space Agency. Let's get to know the main parts of the station. The integrated truss structure is kind of like the backbone of the station. It holds the solar arrays to generate electricity, radiator panels, these remove heat from the station, and other equipment and science experiments are also attached. This part down here contains the pressurized modules, which means the astronauts can live and work in here without a spacesuit. All of the Russian modules make up the Russian orbital segment. The other side is called the United States orbital segment. It's made up of modules from the United States, Europe, Japan, and Canada. The different pieces of the station, also called modules, were built in many locations around the globe. Each module was then launched into space by one of these 3 rockets: the American Space Shuttle, the Russian Proton rocket, and the Russian Soyuz rocket. Once in space, it's time to put it all together. This is definitely not your average Lego set. Once construction started, the ISS took a little over a decade before it was considered complete. Each one of these lines represents the addition of a new module to the station. Let's go ahead and start at the very beginning. The first piece of the station is a Russian module called Zarya. It provides power from the solar arrays and also propulsion when there's a need to move the station. There's 3 docking ports in front and 1 in back. These will be used to connect to the next pieces of the station. The second module is American, and it's called Unity, or Node 1. It has 6 docking ports to connect to future modules. There's a special piece here to connect between the different docking mechanisms. This is called a Pressurized Mating Adapter, or PMA for short. Unity was launched with PMA 1 and PMA 2. This is the Zvezda service module. It provides life support systems and is considered the functional center of the Russian orbital segment. It also has 3 docking ports in front and 1 in back. Next is the Z1 truss. This holds equipment for the station. It's not part of the main truss, but it provided a temporary mounting place, as we'll see here in a moment. PMA-3 was then added to the bottom side of Unity. It's always good to have an extra one of these around. The P6 truss was temporarily mounted to the top of the Z1 truss. This includes the first solar array wings. This provides much needed power to the growing station. Radiator panels were also installed to help remove excess heat from the station. At this point, there was enough functionality that astronauts can start living aboard the station, instead of just temporary visits. From November 2000 until now, there has been a continuous human presence on board the station. The Destiny module is also called the US Laboratory. This is a place where a lot of scientific research happens. A little rearranging was necessary so that Destiny could be installed. March 2001 came the addition of the External Stowage Platform 1, or ESP-1. This was a place to store spare parts for the station. Canada made a vital contribution with the Canadarm2. It's a robotic arm that can help around the outside of the station. It's usually controlled by an astronaut who's on the inside of the station. Either end of the arm can be attached to one of these grapple fixtures that you'll find on various modules. The Quest airlock allows the astronauts to safely step outside for a few hours to perform an EVA, also known as a spacewalk. This is a Russian module called Pirs. It can be used as an airlock for spacewalks or as a docking port to allow visiting spacecraft to attach to the station. Now we get to start building the integrated truss structure. If you remember from earlier, this is kind of like the backbone of the station. Our first piece is the S0 truss, and it gets attached to the top of the Destiny module. The Mobile Remote Servicer Base System, or MBS, was added next. This platform can move along the truss. It's especially useful when the Canadarm2 is attached. Then the S1 truss was added, followed by the P1 truss. The S stands for starboard and the P stands for port. This way you know on which side of the station it's on. Each side has room for 3 more radiator panels. For now, only the center ones will be installed. ESP-2 was added to the station right next to the Quest airlock. This is the P3, P4 truss segments with solar arrays and another radiator panel. The tiny P5 truss goes at the end here. To balance out the station, we'll have to retract a few panels. The following year, the other sides of the truss were added as well. ESP-3 goes down here, and then the P6 truss can be moved to its final resting place. It's also time to deploy a few more radiator panels. The Harmony module is also called Node 2. It will be attached to the forward end of Destiny, but first we have to do some more rearranging. Harmony has 6 docking ports which will allow for further expansion of the station. Next comes the Columbus module, which is a European laboratory. Now we get some more robotics also built by Canada. This is a space robot called Dexter. It can attach to the same grapple fixtures that are used by the Canadarm2. In fact, Dexter is most useful when it's attached to the end of the Canadarm2. The largest module is the Japanese experiment module, also known as Kibo. It came up to the station in several pieces. It even has its own robotic arm. Finally, we have the S6 truss, the last of the truss segments. Now we're starting to look a little more like the space station. These solar arrays will be rotated so that they face towards the sun. This helps the arrays generate more power for the station. The Japanese experiment module has one last addition. It's called the Japanese Exposed Facility. This allows research to be conducted in the vacuum of space. The Russian module Poisk is very similar to Pirs. It was another place for Russian spacecraft to dock. This is the first Express Logistic Carrier, or ELC-1. This is a place to store hardware to help the station work correctly. ELC-2 was installed on top of the truss here. The Tranquility module, also known as Node 3, is added to the side of Unity. On the bottom side of Tranquility is a small room called the Cupola. This has 7 windows from which to see the view. Each window has a cover that can be closed when they are not in use. Then came another Russian module called Rasvet. This was used for storage and as another docking port. The Leonardo module is used for storage of supplies and waste. The trash will build up here until it can be removed from the station. Here's ELC 3 and 4. This is a science experiment called the Alpha Magnetic Spectrometer. It's used to study rare particles such as antimatter. A more recent addition to the station is called the Bigelow Expandable Activity Module, or BEAM for short. It takes up a small amount of space during launch and then inflated once attached to the station. BEAM is an experiment to see if this kind of technology can work. The ISS only has funding through 2025, but hopefully that will be extended. After that, we may see pieces of the station repurposed for other projects in space.
진입장벽 완화와 성공 가능성 제고에 대해서 말씀드리겠습니다. 인류는 우주 기술로부터 막대한 혜택을 받고 있습니다. 인공위성은 국제 공영 네트워크의 연동, 기후 관측, 지속 가능한 자원 관리, 오지에서의 교육 및 핵심 서비스 제공, 자연재해 초기 정보 등 일상생활에 도움을 주고 있습니다. 우주 기술도 다른 많은 부분과 마찬가지로 기술 발전에 의한 거대한 변혁에 직면해 있습니다. 변혁을 통해 더욱 많은 편익을 창출할 수 있으나 우주 부문이 갖고 있는 잠재적인 문제들을 우선 해결해야 합니다. 우주는 최첨단 기술의 영역이라고 흔히들 생각하지만 현실은 이보다 복잡합니다. 1950년대와 60년대 정부의 대대적 투자는 초창기 우주 부분에 혁신을 촉진하였습니다. 이로부터 파생된 기술들은 마이크로칩과 소프트웨어 공학처럼 미래 산업의 밑거름이 되었습니다. 그러나 우주선 발사에 드는 많은 비용과 척박한 우주 환경 때문에 안정성과 성능성을 중시하게 되면서 혁신이 제약되고 진입 장벽이 높아졌습니다. 오늘날 우주 부문에서는 높은 수준의 혁신이 다시 이루어지고 있지만 이는 대부분 다른 부문에서 역으로 파생되어 온 기술들 덕분입니다. 예를 들어 마이크로칩과 소프트웨어 산업은 다음 두 가지 중요한 측면에서 역으로 우주기술 발전에 기여하고 있습니다. 첫 번째는 기술적인 측면입니다. 스마트폰과 노트북 등 기타 컴퓨터 기기 생산 인프라는 보다 스마트하고 빠르며 저렴한 우주 부품과 인공위성을 개발하는 데 일조하고 있습니다. 클라우드 컴퓨팅은 인공위성으로부터 산출된 정보의 처리와 저장을 상용화하였습니다. 3D 프린터, 첨단 로봇공학, 인공지능과 같은 최신 기술들은 인공위성 생산 능력 제한에 대한 고정관념을 깨고 진입장벽을 허물고 있습니다. 메이드 인 스페이스는 프린터 사용 가능성을 보여주었으며 노바웍스는 궤도상에서 자율적으로 조립 가능한 모듈형 위성 부품을 개발하고 있습니다. 다른 파생 효과는 자본과 인적 자원 측면에서 이루어지고 있습니다. 신규 투자 기회를 기다리는 벤처 투자자들과 도전을 원하는 젊고 유능한 엔지니어들은 넘쳐나고 있습니다. 많은 투자자들과 공학도들은 실제 우주인을 보거나 공상과학 소설을 읽으며 우주를 동경해 왔습니다. 목적의식이 뚜렷한 전문가들은 우주 부분에 기여하는 것에 대해서 보람을 느끼고 있습니다. 예를 들어 플래닛사는 전 나사 엔지니어들에 의해 실리콘밸리에서 설립된 많은 우주 관련 스타트업 중의 하나입니다. 플래닛은 IT 업계에 넓은 소프트웨어, 하드웨어, 인재들을 흡수하고 있습니다. 기술, 자본, 인재 유입은 우주 부분에 심대한 변화와 혁신을 유발하고 있습니다. 원격 센서, 정밀 운항 및 타이밍 등 전통적인 우주 응용 기술의 생산성은 더욱 높아지고 있습니다. 인공위성을 설계, 생산, 발사, 운용하는 비용은 점진적으로 낮아지고 있으며 이로부터 얻어지는 데이터의 저장, 처리, 정리 능력은 발전 중입니다. 동시에 저렴한 방식의 인공위성 발사, 우주에서 다른 재화를 생산하는 계획, 우주 자산들의 사용기간을 연장할 수 있는 관리 능력의 향상까지 새로운 우주 활동이 이어지고 있습니다. 그러나 우주 부문의 변화는 기존 문제들을 복잡하게 하고 새로운 문제들을 야기하고 있습니다. 진입장벽 완화와 기술 진보로 많은 국가와 민간 기업이 우주 활동에 참여하면서 인공위성 발사가 수십 배 증가했습니다. 향후 10년간 광대역 인터넷과 다른 서비스 제공을 위해서 10,000대 이상의 상업용 위성 발사가 계획되어 있습니다. 이로 인해서 지구 궤도가 혼잡해지고 있으며 우주 트래픽 추적 및 관리, 궤도상 충돌 탐지 및 방지 등 새로운 문제들이 발생하고 있습니다. 지구와 우주에서 더 많은 대역폭을 원하는 끝없는 욕심 때문에 전자기파 스펙트럼의 무선 주파수 대역도 점차 혼잡해지고 있습니다. 또한 군사 및 국가안보 목적으로 우주 공간 사용이 증가함에 따라 미래에는 분쟁이 지구에서 우주로 확대될 가능성이 높아지고 있으며 이는 미래 우주 공간의 사용을 제한할 수 있습니다. 이와 같은 문제들을 해결하는 것은 불가능한 일이 아니며 이미 해결하기 위한 노력들도 이루어지고 있습니다. 국가들은 양자 및 다자 협의를 통해 중대한 안보 문제에 대해 논의하고 불신을 완화하기 위해 투명성 제고 및 신뢰 구축 조치를 도입하고 있습니다. 또한 우주의 장기적이고 지속 가능한 이용을 위해서 국가와 민간 기업이 협력하고 있습니다. 우주 잔해 최소화, 우주 상황인식 제고, 궤도상 충돌 방지 등이 여기에 해당됩니다. 그러나 향후 인류가 우주로부터 최대의 혜택을 얻기 위해서는 국제사회가 더욱 노력해야 됩니다. 우주기술 발전을 위해서 다음과 같은 분야에서 혁신적인 리더십과 거버넌스가 요구됩니다. 첫째는 국제 규제 프레임워크에 민간 기업의 참여를 확대할 수 있는 메커니즘을 형성하는 것입니다. 둘째는 우주 광물 개발 및 민간 기업 활동과 관련해서 국내 및 국제 규율에 조정이 필요합니다. 민간 자본의 투입이 증가됨에 따라 각국 정부는 민간 기업이 우주 활동과 관련해서 국제법의 테두리 안에서 국내법을 준수하도록 보장해야 합니다. 셋째로 새로운 우주 트래픽 관리 시스템이 도입이 필요합니다. 우주 영역에 참여하는 사람들이 늘어나면서 지구 궤도에 있는 물체들을 관리할 수 있는 더욱 체계적인 시스템이 필요합니다. 넷째로 우주의 잔해를 완화하려는 이행 노력이 필요합니다. 현역 및 퇴역 인공위성과 로켓 잔해들의 관리와 관련하여 개별적인 가이드라인은 현재 있으나 모든 행위자가 지구 궤도를 보호하도록 하는 이행 메커니즘은 아쉽게도 존재하지 않습니다. 다섯째로 일부 국가에서 우주 관련 활동을 통제하기 위한 필요한 메커니즘이 필요합니다. 새로운 국가나 단체가 우주 영역에 진입하면서 예측지 못한 충돌이 일어날 수 있습니다. 모든 국가가 확립된 우주 관련 행동 지침을 따르도록 하는 확실한 메커니즘이 절실합니다. 어펜딕스입니다. 지금까지 시청하신 것으로 이번 차수 수업이 인정됩니다. 스페이스 테크놀로지와 관련한 동영상을 보도록 하겠습니다.
You have probably seen a picture of Elon Musk's latest project, a rocket that looks like the brainchild of a H.G. Wells fever dream of the future. It doesn't look like any current generation rocket by any shape or measure. It's shorter and fatter than your typical SpaceX rocket, and most strange of all, it's made of stainless steel, a material that has largely fallen out of use for propellant tanks since the 60s. Steel is strong, but it's pretty heavy, making it unsuitable for flight structures. Reducing the weight of the launch vehicle is an art form in rocket science. Every kilogram matters, and engineers have come up with some innovative ways to reduce weight. WD-40 was originally developed to displace water, which is where its name came from, to protect the metal tanks of the Atlas rockets from rusting, because they weren't painted to save weight. Those Atlas rockets were made of stainless steel. In those days, aluminium alloying material science hadn't quite developed far enough, and the engineers of the Atlas rockets instead opted to use extremely thin stainless steel for their propellant tanks, varying from 2.5mm to about 10mm. These were essentially metal balloons, as they were structurally unstable when unpressurized. In one infamous case on May 11, 1963, an Atlas Agena D lost pressurization on the launch pad, allowing the weight of the upper stage to buckle the thin steel. Pressurization adds strength to pressure vessels as the pressure provides a restoring force for small deformations. So, if the metal attempts to bend inwards, the internal pressure pushes it back out. This strengthens all rocket tanks, allowing their thickness to be minimized, but this application took it to the extreme to make up for steel's density. Our choice of material for aviation and aerospace applications has evolved with our mastery of material science, specifically with the materials available to us that have the highest strength to weight ratios. We can visualize these strength to weight ratios on a graph like this, plotting the strength of the material against its density. Looking at this, it's pretty clear that steel adds a significant amount of weight while not adding a proportional amount of strength. Steel is typically 2.5 times heavier than aluminium, but it is not 2.5 times stronger. So why use stainless steel? Well, strength to weight ratios are not the only factor engineers have to consider. Something you may not consider are things like thermal conductivity. Aluminium has a much higher thermal conductivity than steel, and thus can conduct heat from its surroundings into the cryogenic fuel much faster. This can vaporize the fuel, which requires boil-off valves to vent the vaporized fuel. To minimize this problem, rocket fuel tanks are often sprayed with foam insulation. That's what gave the external tank of the space shuttle its distinctive orange color. But this adds a substantial amount of mass itself, which in turn decreases the weight-saving benefits aluminium provides. However, the Falcon 9 fuel tanks are not insulated. To prevent major boil-off of the fuel is loaded as late as possible. This reduces the amount of fuel that will be vaporized, but also makes the job of getting the Falcon 9 certified for human payloads a bit of a nightmare. NASA did not want SpaceX to fuel the rocket with passengers on board, because, as we saw earlier, things can go wrong during that phase. In August 2018, they finally approved the Falcon 9 for this load and go style of fueling for human flight. The aluminium-lithium alloys used in the Falcon 9 were not developed until the late 50s and early 60s, which increased their strength to weight ratios, allowing their introduction to aerospace applications. The stainless steel balloon tanks of the Atlas rockets were eventually made with this aluminium alloy metal, and their strength to weight ratios were boosted by using a unique stringer pattern called an isogrid, which boosted the aluminium's ability to resist buckling, like that of the Atlas Agena D. NASA performed these huge compressive buckling tests on the aluminium-lithium tanks of the SLS rocket. Typically, you use little strain gauges whose electric resistance changes as you stretch them, forcing the electrons along a longer path to keep track of the strain in the material. But for something this big, they would have needed thousands. Instead, they painted dots all over the structure to allow computer imaging software to keep track of the strain. That isogrid structure is excellent for maximizing strength while minimizing the material needed. It is essentially an interwoven pattern of I-beams that increase the stiffness of the overall structure. You will see this pattern everywhere in aerospace, from these 60s era rockets to SpaceX's new Dragon 2 capsule. SpaceX to date has used aluminium-lithium alloys in their propellant tanks, but they opted not to use this isogrid structure. Even though it provides fantastic strength to weight performance, it is absurdly expensive to manufacture. To manufacture isogrids, you start off with a thicker piece of aluminium and machine it down using a CNC machine. This results in about 95% of the material going to waste. Instead, SpaceX opted for a thin skin of aluminium-lithium alloy and then stir-welded strengthening stringers in place. We are constantly balancing a huge number of factors. Here, the cost of manufacturing the rocket influenced its design. Typically, the cost of launching an extra kilogram of material to space far outweighs the cost of material, but in cases like this, the waste in manufacturing process can influence material choice. For example, Musk attributed the cost of carbon fiber composites as one of the primary reasons he abandoned it as a material for the Starhopper. Carbon fiber composites cost about $135 per kilogram, and a significant amount of that is thrown away in the layup process. The manufacturing process for carbon fiber composites is extraordinarily expensive and difficult. As explained in my carbon fiber video, carbon fiber composites gain all of their strength from the long and thin carbon fibers inside the plastic resin that holds them together. This means that their strength is not the same in all directions. And in order to ensure the material can be strong in all directions, you have to layer your carbon fiber composite in a very specific way. You then have to cure it in a pressurized oven. This was one of the major flaws I pointed out in predicting the failure of the early prototypes of the BF4 carbon composite tanks, which were made in two parts, presumably because they couldn't find tooling and an autoclave big enough to cure a full-sized tank. Being perfectly honest, this is the only subject area where I have enough expertise to make comments on other people's designs, and I was surprised SpaceX was pursuing the material at all, for the reasons stated above, and as it's unsuitable for a vehicle that not only has to withstand the freezing temperatures of the cryogenic fuel on ascent, but the scorching temperatures of re-entry, not once, but twice, as this will be the first vehicle in history expected to visit Mars and return. Here we really start to see where stainless steel shines and why Musk is opting for a stainless steel vehicle. Let's plot another graph, this time plotting strength against maximum operating temperature. Here we can see that stainless steel outperforms both aluminium alloys and carbon fiber composites by a significant margin. The Falcon 9 first stage serves only to boost the second stage to about 65 to 75 kilometers in altitude and between 6,000 and 8,300 kilometers per hour, before flipping over and performing re-entry burns to slow down before entering the thicker atmosphere at relatively slow speeds. Even then, the engine nozzles, which are designed to tolerate massive temperatures, take the brunt of the re-entry heating, allowing the aluminium tanks to avoid any major re-entry heat. This is not how the Starhopper is intended to work, because it is being built as an interplanetary vehicle. The Starhopper can expect to enter the Martian atmosphere at speeds of up to 21,000 kilometers per hour and experience temperatures up to 1,700 degrees, well above the maximum service temperature of both aluminium and stainless steel, but we have ways of leaching some of that heat away before it can heat the metal. The Curiosity rover utilized a phenolic impregnated carbon ablator, which is extremely light, has a low thermal conductivity, and can resist extreme temperatures of up to 1,930 degrees. But nothing this heavy has entered the Martian atmosphere before, and it's not going to be an easy task for it to slow down. It's going to have to enter the Martian atmosphere at an extremely high angle of attack to allow the thin Martian atmosphere to sap away speed through drag for an extended period, but drag comes with heat. Stainless steel may be heavy, but it will require significantly less heat shielding than an aluminium or carbon fiber composite, once again closing that weight advantage gap of these alternate materials. In fact, Musk has stated that the rear side of the Starhopper will require no heat shielding at all, and he plans to use a strange technique to cool the wind-facing side of the vehicle, using the same method humans use to cool down, by sweating. Musk plans to pump liquid methane between two steel panels on the windward-facing side of the SpaceX rocket, where it will gain heat, vaporize, and evaporate through small holes in the rocket's surface. This is a pretty weird way of cooling a ship, and I wondered why you would not just opt to use the tried and true method of a blade of tiles. Then I remembered that this ship needs to make a return journey, and the entry into the Martian atmosphere will damage the tiles and require maintenance. There is no oil on Mars to manufacture new phenolic resin or the carbon needed for ablatives, so using methane, the fuel the new Raptor engines that SpaceX will use for the Starhopper, makes a lot of sense. It reduces the equipment the rocket will need to carry to Mars, making the rocket significantly lighter. They can just use the equipment they already needed for refueling, making it double purpose. They just need to mine water and extract carbon dioxide from the atmosphere, and then do some fancy chemistry to produce methane and oxygen. The prototype they are building at the moment is likely just to test the manufacturing techniques needed to build it and test its flight capabilities.